So previously we talked about why we need algorithms to tune automatically. It's because spin qubit arrays and quantum dot arrays are getting more and more complex, and you need a kind of quite a few gate electrodes to tune even a single qubit to a well-controlled qubit. And so, if you want to do that for a larger array, you will probably need some kind of automation because doing it by hand will rapidly get very boring. So we covered why we need these algorithms. Now let's see how what those algorithms might look like and what we can rely on and what parts we can automate. So one example from Iana Darulova that's been published in PhysRev Applied recently used a method to do it which goes in a kind of flowchart and tries to do successive levels of vetting of the device to figure out if the device will indeed make a good qubit at all. And at the end, it tries to then, knowing that it is a good qubit, use the information gleaned from previous steps to actually tune those gates such that you trap the correct number of electrons. Let's go through it a little bit slowly. So first, you would load a device into your fridge and you would do some quick tests. One test that we would always do is to do a gate leakage test, which is to tell if your gate is functioning properly or whether it was blown up, perhaps during bonding or some other time, or whether it is, touching some other gate, in which case those two would not be independent gate voltages you can work with. The second test you would do is a kind of initial quality assessment. This can take the form of many things depending on what kind of qubit you have. For example, you could test if you can actually form a channel, if you can actually draw up a sea of electrons that you can then shape into your qubit array. And you can even check if your gates are doing the right thing and if your lithography looks like it looked when you drew it out in PowerPoint, for example. The next thing you would do is start checking your gates. First of all, you would do 1D scans. You would do 1D scans because these are relatively cheap to carry out and the data involved is easy to analyze and fit to. So if you do 1D scans of each gate, then you can find out about each gate's functionality and also something called the lever arm, which is how much of an effect it has on the quantum system if you move it by a fixed amount, let's say 100 millivolts or something. Some of these scans would look like these pinching off type scans. And some of these would maybe not look so good and would not pinch off so cleanly. And so, what you can do then is you can have a sort of binary classifier where you set some, let's say, perhaps in the beginning, arbitrary threshold, which says that the quality of this particular gate is maybe not good, but the quality of this particular gate, which pinches off cleanly, is good. And then you use this binary classifier to then classify your devices into good or bad, or devices that you go further with and devices that you do not go further. And it turns out that you actually can use a lot of code, for example, Python's scikit or Keras or other libraries that other people have written for other applications, because a lot of the problems for auto tuning and quantum devices can actually be reduced to or be analogous to other problems that people have faced with other kinds of data. Once you've selected these working devices, now you can go to the next step, which is tuning them to the correct regime. And here you would use the information you have gleaned already in step 2, which is where you found out about each gate's functionality and their lever arm or their effect on the quantum dot. And you can use this to count electrons and trap the required number of charge states. And the thing that actually lets you do this is the fact that a single quantum dot, if you remember when we talked about it before, has a different pattern of lines. They are kind of diagonal, for instance, than a double quantum dot, which would have a kind of honeycomb pattern, for example. And you can use this to trap the required number of electrons. and you can proceed with further tuning into the single or double dot regime. A little more detail on how you would recognize a single and double dot regime. Let's say you have a device which in design looks like this. Uh, mm, Importantly, you have a left plunger and a right plunger which control the number of electrons in your left quantum dot and your right quantum dot. If you have set your center barrier, the blue gate here, very negative, then you can assume that you have two uncoupled quantum dots which are not interacting with each other. And now, if you start mapping out how the current, let's say, going through the system will look like, you can see that it will have a kind of pattern where as you go around along the x-axis, you're adding charges to the left dot, while if you are going along the y-axis, you are adding charges to the right dot. Now, when you change both gates, you can at will trap n or m electrons. You just need to know where in this pattern you are. And something that humans, but also coincidentally computers, are very good at is actually this kind of pattern recognition. If you want to look at more about these, how these patterns are generated and how it works, this is something called the constant interaction model. You can look at previous QTech videos. Another thing that happens is that quantum dots can interact capacitively, where these gates have a capacitance to each other's quantum dot and also the dots cross capacitance. And so if you start letting capacitance interaction happen, when your central barrier gate electrode is less negative, then you see that those lines that were straight lines before, completely non-interacting, are now slightly bent. And this is, you can also recognize. So by looking at your pattern, seeing whether it's completely flat or has a bend, you can already recognize, or the computer can already recognize, that you are in a particular regime. If you now take your central barrier electrode and make it even less negative, so you're letting the electrons interact even more, then what happens is that a different pattern appears. What is happening is that electrons can now tunnel between quantum dots, and their wave functions can now overlap near new lines. These are called interdot charge transition lines. And what happens at these points is that you have lowered your gate barrier, your central middle gate barrier, and it means that the overlap of the electrons' wave functions can now take place. And actually, for a qubit, especially for spin qubits, such an overlap can already introduce a quantum gate, a 2-qubit gate between two single electron qubits. So these points in in gate voltage space are extremely important points for electronic interactions. And so if you want to do quantum gates, you better know where these are located. And interestingly, by looking at such a pattern, you can always kind of map out this honeycomb and figure out where are the points where you need to load your electrons. This would be by crossing these lines or these lines, or where you need to go if you want to make your electrons interact and do a gate. These would be these interdot charge transition lines. And now you can see how they did the regime prediction using binary classifiers. You could look at those patterns, which I bet you can already do after watching this video, and say which ones are in the single dot regime, which ones are in the double dot regime, and which ones are in the interacting or non-interacting.